You know, corrosion, it's this silent, relentless enemy that costs our global economy something like $2.5 trillion every single year. It's what brings down bridges, it's what bursts pipelines, and it's what turns shiny new cars into piles of rust. Now, to fight it, to actually beat it, we first have to understand it. We have to get into its science. So let's dive right into the core theory that makes all corrosion protection, especially cathodic protection, possible.
We're going to build this thing from the ground up. First up, we'll take apart that tiny little electrochemical engine that causes all the trouble, the corrosion cell. Then, we'll get into what actually powers it and what environmental triggers kick the whole thing off. After that, we'll figure out how to measure the destruction it leaves behind. And finally, we'll explore what slows it down and all the different shapes and forms it can take. All right, let's get started.
You have to realize every single spot of rust you've ever seen, every pit in a pipeline, it all starts with this one single concept: the basic corrosion cell. Think of it like a tiny little engine of destruction, and it's got 4 essential parts that all have to be there for corrosion to even get started.
And this diagram right here, this is the heart of it all. The best way to think about it is like a tiny, destructive little battery. You've got 4 key players on the field: an anode, which is where the metal actually dissolves; a cathode, which is the part that stays protected; an electrolyte, which is kind of the conductive soup they both sit in; and a metallic path for the electricity to flow. Now here is the most important takeaway of all. If you can remove any one of these 4 components, you break the circuit, and corrosion just grinds to a halt. That right there is the fundamental principle behind almost all corrosion control.
So, let's start with the anode. This is where the action happens. And, this is where the damage happens. It's the part of the metal that is actively sacrificing itself. It literally gives up tiny particles of itself, we call them ions, into the electrolyte. And in doing so, it releases electrons. This chemical reaction has a name. It's called oxidation. And oxidation is the very definition of corrosion. So all those electrons that the anode just released, well, they have to go somewhere, right? They travel along that metallic path to our second component, the cathode. Now, the cathode is the protected site in this little circuit. It's the good guy, so to speak. It accepts and consumes the electrons in a different reaction called reduction. The key here is no metal is lost at the cathode. In fact, the cathode is what the anode is corroding to protect. Okay, so we've got electrons flowing from the anode to the cathode through the metal. But what about those metal ions that dissolved from the anode? They need to complete the circuit too, and that's the job of the electrolyte. This isn't like a wire, it's any substance that has ions in it that can conduct electricity. Think soil, seawater, or even the moisture that's trapped in concrete. It's basically the highway for ions, connecting the anode and cathode and letting that whole electrochemical reaction keep on running.
And the final piece of our puzzle is the metallic path. This is the physical connection, the wire that lets the electrons actually get from the anode to the cathode. Now, it could be a literal wire, but more often than not, it's the metal structure itself. You know, the body of a car, the girder of a bridge, or the wall of a pipeline. So once you have all 4 of these things in place, anode, cathode, electrolyte, and metallic path, you've got yourself a complete, current-flowing, metal-eating circuit.
So what makes this circuit run in the first place? What's the driving force? Well, it all comes down to something called electrical potential. The easiest way to think about it is like water pressure. The bigger the difference in electrochemical potential between 2 different metals, the more pressure there is pushing that corrosion to happen. And to understand that pressure, we start with this table right here, the standard EMF series. Think of it as a theoretical ranking, a league table, of how willingly different metals give up their electrons, but under perfect, sterile lab conditions. It ranks them from the most noble or stable, like gold, way up at the top, down to the most active or reactive, like magnesium at the very bottom. And here's the key. The more negative that voltage number is, the greater that metal's natural tendency is to become the anode and corrode when you connect it to any metal above it on this list. But here's the thing. We don't work in a lab, do we? The real world is messy. It's wet, it's dirty. And that's why for us, we have the practical galvanic series. It takes the same idea, but it ranks metals based on their actual measured potentials in a specific real-world electrolyte, like seawater. For any field technician, this is the guide that really matters.
Now, this is where this whole concept becomes an incredibly powerful tool for predicting what's going to happen. This is a practical galvanic series for seawater. And here's how it works. You can pick any two metals on this list, and the one with the more negative potential, so the one that's higher up on the chart, will always become the anode and corrode if you connect them electrically in seawater. So for example, if you connect clean steel, which is sitting around minus 0.5 volts, to copper at minus 0.2 volts, guess what happens? The steel will rust away to protect the copper. And that, my friends, is the basis of galvanic corrosion.
Okay, so those galvanic series tables are awesome for a specific environment, like seawater. But what if your pipeline is buried in soil that has a totally different ion concentration? Or what if it's operating at a higher temperature? We need a way to adjust those standard lab values for real-world conditions. And that is the power of the Nernst equation. It's the formula that lets us fine-tune our theoretical predictions for the messy, complicated reality we find out in the field.
Now don't let all the symbols scare you. Let's just break this down piece by piece. The E on the left, that's what we're trying to find, the actual, real-world electrode potential. E0 or E0 is our starting point. That's the standard potential we pull from a reference table like the EMF series. The rest of this equation is basically a big correction factor. R is a constant, and T is the absolute temperature. That right there tells us that temperature directly affects potential. N is the number of electrons being transferred in the reaction, basically the metal's valence. F is just another constant, Faraday's constant. And that last part, with the A values, that accounts for the concentration or activity of the ions in whatever solution we're in. So in short, the equation takes a lab value and then it systematically adjusts it for the real-world temperature and chemistry.
So how would a corrosion tech actually use this? Let's walk through it. Step 1, you'd look up the standard potential for zinc, which is minus 0.763 volts. Step 2, you'd figure out how many electrons zinc gives up when it corrodes, which is 2. Step 3, you'd measure the concentration of zinc ions in your specific electrolyte. Let's just say it's a 0.01 molar solution for this example. And finally, step 4, you just plug all those values, the standard potential, the number of electrons, the temperature, the concentration, into the Nernst equation to calculate a really precise real-world potential for zinc in that specific environment.
So it's not always about connecting two different types of metal together. The environment itself is an expert at creating corrosion cells, even on a single uniform piece of metal. Little variations in temperature, stress, and chemistry can create thousands of tiny anodes and cathodes all over a structure.
Take temperature, for example. Just a simple difference in heat across the very same piece of metal is enough to create a corrosion cell. As a general rule, the hotter area becomes the anode and starts to corrode. The diagram shows a hot pipe coming right out of a compressor station. Well, that hot section becomes anodic to the cooler pipe further downstream. The exact same thing happens in a well casing, where the warmer, shallower part corrodes to protect the cooler, deeper section below.
You know, the way we actually manufacture metal parts can also bake corrosion problems right in from the start. When we alloy different metals together, or bend a pipe, or weld two pieces of steel, we create these areas of really high internal stress. Think of it like a tightly wound spring. It's just storing energy. These high-energy, stressed-out zones have a much greater tendency to become anodic, and they'll corrode much more easily than the less stressed areas right next to them.
But you know, one of the most common and sneakiest environmental triggers is something called a concentration cell. Now, in this case, the metal itself is perfectly uniform. The problem is that the electrolyte touching it isn't. A simple difference in the concentration of some chemical, like oxygen or salt, from one spot to another is all it takes to create a really powerful anode and cathode.
Let's look at the most common type, an oxygen concentration cell. The rule here is simple. The area with less oxygen becomes the anode and corrodes. This is exactly why a crevice, which is starved of oxygen, will start to rust first. A perfect real-world example is a pipe that's buried under pavement. The section directly under the pavement just can't get as much oxygen from the air as the section in the open soil next to it. So what happens? The oxygen-starved section under the pavement becomes the anode, and it starts to corrode away.
And this same logic applies just about everywhere. If you have a pipeline that passes from sandy, well-aerated soil into a dense, oxygen-poor clay, the section in the clay becomes the anode. Or, if a section of pipe is exposed to higher salt concentrations from road de-icing in the winter, that salty section will become anodic to the rest of the pipe.
All right, so we know what causes corrosion, and we know where it happens. But the big question is, how fast is it happening? How can we actually quantify the damage? For that, we need to turn to the laws of electrochemistry and some pretty essential field tools.
This brings us to one of the most important principles in our entire field, Faraday's law.
This is not just some abstract formula, okay? This is the fundamental law that gives us a direct, predictable, mathematical link between that invisible flow of electricity and the very real physical loss of metal. It means that if you can measure the corrosion current, Faraday's law lets you calculate exactly how much weight in metal is being lost over any period of time.
So let's look at the components. W is the weight of metal lost. That's what we want to find. This weight is directly proportional to three things. M, which is the atomic weight of the specific metal we're dealing with. I, the corrosion current flowing in amperes. And T, the time in seconds that the current is flowing. The bottom part of the equation just tells us it's inversely proportional to N, the number of electrons the metal transfers, and F, that Faraday's constant again. It's a really beautiful direct relationship. More current and more time simply equals more metal lost.
Now, the real power of Faraday's law is that it lets us pre-calculate this cheat sheet of electrochemical equivalence. And this table is incredibly useful for a corrosion engineer. It tells you, for example, that if you measure 1 amp of corrosion current on a steel pipeline, you know for a fact that you are losing exactly 9.13 kilograms, that's about 20 pounds, of steel every single year. This lets us translate an electrical reading from a multimeter directly into a rate of physical damage, which helps us predict when a repair or a replacement might be needed.
But to make those electrical measurements out in the field, we need a stable, reliable reference point, right? You can't just stick one probe of your voltmeter onto a pipe and the other one into the dirt because the soil's potential is changing all the time. That's where this guy comes in, the copper-copper sulfate electrode, or CSE. It contains a specific chemical solution that gives it a constant, known potential. So by measuring the voltage difference between our pipeline and this stable reference, we can get an accurate, repeatable reading of the pipeline's structure-to-soil potential.
Now here's an interesting thing. Corrosion doesn't just run wild at its maximum theoretical rate. The process itself actually creates a kind of back pressure, or resistance that naturally slows things down. This whole phenomenon is called polarization, and understanding it is absolutely critical for corrosion control.
Okay, let's break down this Evans diagram, because it's a really powerful way to see what's happening. The top red line, that's the natural or open circuit potential of the cathode, and the bottom blue line is the natural potential of the anode. Now, in theory, the voltage difference between them should be huge. But as soon as you connect them and current starts to flow, something happens. Their potentials start to shift or polarize toward each other. The point where they finally meet, right in the middle, that's the actual mixed potential you would measure on the corroding structure. And here's the most important part. If you look straight down from that intersection point to the horizontal axis, it tells you the real-world corrosion current, labeled here as I-core. The entire goal of corrosion control is to manipulate these lines to make that I-core value as small as humanly possible.
So why does this slowdown even happen? Well, there are two main types of polarization. The first is activation polarization. Just think of it like a traffic jam right at the toll booth. There's a bottleneck in the electrochemical reaction itself, like transferring the charge at the surface is just really slow. The second type is concentration polarization. In this case, the toll booth is working fine, but the road leading up to it is empty. The reaction is literally being starved for raw materials, like maybe not enough oxygen can get to the cathode, or the products are piling up and clogging the exit. Either way, the whole process slows way down.
And of course, lots of things in the environment can affect how much polarization happens, basically controlling the speed dial of corrosion. Higher temperatures or a faster flow of water, for instance, can deliver reactants more quickly and reduce that concentration polarization, which speeds up corrosion. The density of the current and the concentration of ions in the electrolyte, they also play a huge role in determining what that final corrosion rate will be.
Now, one of the most critical factors of all is the ratio of the cathode area to the anode area. And the point on this slide is absolutely vital. A small anode connected to a large cathode is the absolute worst-case scenario you can have. Imagine a tiny little scratch or defect, we call it a holiday, in a pipeline's protective coating. That tiny exposed spot of steel becomes the anode, while the entire rest of the huge, coated, protected pipe can act as the cathode. All of the corrosion energy gets focused on that one tiny pinprick. This creates an incredibly high current density, and that leads to rapid, deep pitting that can punch a hole right through the pipe wall in no time flat. It's incredibly dangerous.
Okay, for our final section, let's move from the theory to what we can actually see. Corrosion doesn't always look the same. Depending on the metal, the environment, and the specific mechanism at play, it can show up in several very distinct forms.
Depending on the conditions, this attack can take many forms. You might see a uniform attack, where the metal loss is just spread evenly across a big surface. Or you could see galvanic corrosion, where two different metals are touching. Pitting, which we just talked about, is especially nasty because it creates those deep, localized holes. Crevice corrosion loves to hide in tight gaps. Intergranular attack actually follows the grain boundaries inside the metal's crystal structure, and environmental cracking is a really dangerous combination of stress and a specific corrosive environment that can cause a sudden, catastrophic failure.
And this brings us to a final and very critical warning about fighting corrosion. The main technique we use, called cathodic protection, involves making our structure more electrically negative to stop it from being an anode. But it turns out we can go too far. As this quote from the NACE manual warns, if we apply an excessive negative voltage, especially to high-strength steels, we can cause a side reaction that generates hydrogen atoms right on the steel's surface. These tiny little atoms can actually seep into the metal and make it brittle. It's a dangerous phenomenon called hydrogen embrittlement. It's a classic case of the cure potentially causing another, even worse disease if it's not applied correctly.
So there we have it. We've deconstructed the engine of corrosion. We understand its 4 essential parts, the electrical forces that drive it, the environmental triggers that set it off, and the different forms of attack it can take. We have, for all intents and purposes, met the enemy. So the question now becomes, how do we use all this knowledge to fight back? How can we manipulate this electrochemical cell to our advantage, slow it down, or even reverse it to protect our structures? Well, that is the science of cathodic protection, and that's exactly what we're going to cover next time.